In this segment, we're going to look at some of the descriptive properties of the different sections of the periodic table. So from a general standpoint, we look at the periodic table and we say that toward the left side are our metals, the upper right-hand corner, so I'm not sure how well you can see this, but the ones that are in blue are our nonmetals, and then anything along this jagged line here has the potential to be what is referred to as a metalloid, so something that would have properties of both metals and nonmetals. And in this chart, they give certain ones: the boron, silicon, germanium, arsenic, antimony, tellurium, astatine, are specific metalloids. However, as I talked about in class, the best way to think about this is that if you think about the metals as being like kind of a red color and the nonmetals being an orange color, that border between the red and the orange is almost impossible to tell when one starts and the other one ends. So you kind of think of it as a blending of the properties in that area. The one other thing I'd like to point out is hydrogen. Right, hydrogen, traditionally is kept over on the left-hand side of the periodic table with the metals. However, it is generally considered to be a nonmetal. We'll see properties, some of the properties of hydrogen where it behaves like a metal, but it's mostly considered as a nonmetal. The chart at the top here has all of the properties of metals versus nonmetals. You can find this table in your book, but you should have a good understanding of all of these things: the shiny or luster of the metal, the silvery color, whereas nonmetals tend to be dull or lackluster and have actually a variety of colors to them. Metals are malleable and ductile, meaning that they can be bent and pulled into wires, whereas solids in the nonmetal state, or the nonmetals in the solid state, tend to be very brittle. Then we look at the conductivity of heat and electricity, which metals are definitely known for. And then we look at nonmetals, and these are relatively poor conductors of heat and electricity. The metal oxides are usually ionic solids, and we're going to see some of the reactions of those as we go through. The nonmetal oxides are molecular substances, and they're usually going to form acid solutions, and we'll see examples of those also. And again, metals tend to lose electrons and become cations. Nonmetals tend to gain electrons and become anions or oxyanions for the polyatomics. So you can see down here some of the common charges of the different metals in the blue on the left and the nonmetals up in the upper right-hand corner. And then we have a typical reaction here: aluminum reacting with chlorine, and of course the aluminum is going to want to lose 3 electrons, so it's got that 3+ charge here. So if we lose 3 electrons from aluminum, and each chlorine is going to try and gain 1 to become chloride. So the combination there to make this neutral, we would have AlCl3 in the solid state. And then balancing the equation, we need to put a 2 in front of here, 3 and 2. Let's start with the reaction of metal oxides combining with water to form bases. So the base that would be formed here would be magnesium hydroxide. And in the second reaction, we would form lithium hydroxide. For nonmetal oxides, we're going to end up forming acids. So in this first one, we've got P4O10, and that's going to react with water to form phosphoric acid. Aqueous. carbon dioxide gas and water will form carbonic acid. And then carbon dioxide with any kind of base will form water. And I've left out the sodium ion here, but in addition to the water, you would have a carbonate. So sodium were the ion that was associated with the hydroxide here. We would form sodium carbonate. Aqueous. We're now going to take a look at the active metals. The active metals are going to be our first two families in the periodic table. So they're the alkaline metals, which are listed up here, and then the alkaline earth metals, which we'll get to in just a moment. Now, this table, again, is from your text, so you can take a look at this. You notice that the melting point tends to decrease as you go down the family. The density, however, increases. The atomic radius gets larger. You have more principal energy levels. And the first ionization energy is going to decrease, so it becomes easier and easier to remove that loosely held electron. Notice that the francium isn't listed here, so we'll talk about that a little bit later. You can do some research. It's basically because francium is more or less of a radioactive substance, very unstable, so it's difficult to get an accurate measurement of the ionization energy. So here's some reactions with the alkaline metals. So we have sodium with hydrogen forming sodium hydride. Potassium, likewise, would form potassium hydride. We go on down to the reaction with sulfur here, and we would form lithium sulfide. Okay. So mostly what this is showing is that the alkali metals are going to form positive 1 ions when they react. Here we have the alkali metals reacting with water. When they react with water, they're going to form bases. So it would be the sodium hydroxide aqueous plus hydrogen gas. Likewise, potassium hydroxide plus hydrogen gas. And we're going to skip the balancing of these for right now. If we look at the reaction with oxygen, it gets a little more interesting. When we react the alkali metals with oxygen, we get, to start with, we get what we expect. So we would have lithium as a +1, so it would be Li2O. So we have lithium oxide produced. However, something interesting happens when we get to the sodium. With the sodium reacting with oxygen, we get sodium peroxide. So the sodium is still giving up 2 electrons, but now it's giving up those electrons. You need two sodiums will be with the 2 oxygens, making the peroxide. And then finally, potassium will make potassium superoxide. So again, the sodium peroxide, the oxygen's oxidation state's a -1. Here we have oxygen with a 1 minus, oxygen with a 2 minus, and in the potassium superoxide, we have oxygen as a 1/2 minus. Each oxygen only gets half of an electron. Next, we have the alkaline earth metals, again, the active metals. And you can see up here that they all have N and an S2 for the electron configuration. Melting point similar to the alkaline metals decrease as you go down the family. Density increases. Atomic radius also gets larger. And the ionization energy gets smaller as you go down. Again, this table is in your book. No need to memorize those values, but you do need to know the trends. If we look at the reactivity of the alkaline earth metals, excuse me. First we have the reaction with water. Now the alkaline earth metals are not nearly as reactive as the alkali metals. As a matter of fact, the beryllium, when you put that in water, you will get no reaction. So that those two will not react at all. Magnesium reacts very slowly with water, and if you heat the water up and then create a little bit more of a steam type of thing, you're going to form magnesium oxide and hydrogen gas. Okay, but again, it's going to happen very slowly, so it'd be very difficult to detect that hydrogen gas that's produced. Calcium and water, however, the calcium is going to be much more reactive. It's lower down, so the ionization energy is lower because of the increased distance that the electrons are away from the nucleus. Here, you're going to form calcium hydroxide. Usually aqueous, and hydrogen gas. And in this case, you could actually collect the hydrogen gas. This reacts violently enough that that hydrogen gas could be collected and tested with a flame test. The reaction with the chlorides is pretty standard. Magnesium with chloride, again, would form magnesium chloride, again, showing that the alkaline earth metals tend to lose 2 electrons. And then the reaction with oxygen, MgO, solid, again, showing the magnesium tends to lose 2 electrons. And don't know why that's there. We can get rid of that. Hydrogen becomes kind of an interesting element. If we look at the electron configuration for hydrogen, hydrogen is going to have a 1s1 electron configuration, which means that it could either lose an electron, much the same way that nonmetals do, or it could gain an electron the way that, it could either lose an electron similar to what metals do, or it could gain an electron, which makes it similar to nonmetals. Under ordinary conditions, it happens more like behaves more like a nonmetal. However, it does behave, metallic in characteristic, particularly under high pressures. Our most common, or not most common, but the most recognizable reaction of hydrogen is with oxygen, forming water. And actually, the way this is written, it should be in the delta H that's given there is for water in the liquid state. And that would be for the balance equation. But you can see that it actually gives off a significant amount of energy when we react hydrogen with oxygen. Of course, this is the reaction that happened when the blimp exploded over Lyndhurst, New Jersey. Next up, we're moving into the nonmetal section. So we have our oxygen family. One of the most critical reactions or important reactions to us is the reaction of oxygen gas to form ozone gas. Right, this happens in the upper atmosphere, and the energy that's provided to do this usually comes from the sun, and the formation of the ozone creates an ozone layer which helps filter the ultraviolet rays from the sun. Oxygen can very easily be generated from the reaction of, or the decomposition of hydrogen peroxide. In that reaction, you form water and oxygen gas. Okay. And you can see that is an endothermic reaction, so that will give off energy or heat when it happens. And then finally, we have a reaction of sulfur with oxygen. And in this reaction, we're forming sulfur dioxide. So this is that rotten egg smell that some of us will experience or know about. The second blast family in the periodic table are the halogens. And so we have some reactions up here for those as well. So if we react water with the halogens, we're going to create the hydrogen compounds of those. So hydrogen fluoride and oxygen gas. If we react the fluorine with silicon dioxide, we'll get the silicate, so SiF4. And at the temperatures that this happens, it would probably be in the gaseous form, as well as, again, oxygen gas. If we react chlorine in the same way as the fluorine up in the top, we're actually going to get a couple of compounds. We're going to get the hydrogen chloride, but we're also going to get hypochlorous acid, HClO. This is oftentimes used in swimming pools. The hypochlorous acid or the hypochlorite ion is a very good disinfectant for pools. So they tend to put chlorine in pools for that to occur so you don't have any germs building up in the pool. And finally, just kind of our general formula. If we react any hydrogen with any of the halides, we get hydrogen with that, oops, sorry, this is general form HX. So that's in the gaseous state if it's not in water. Finally, we have the noble gases, and again, we can see that these all end with the same electron configuration in their valence shell, that S2P6. Boiling points increase as you go down. The elements are getting larger, so we'll talk about intermolecular forces later on, but as the size of the atom gets larger, the boiling point obviously goes up. Density is going up as you go down. The radius is going up as you go down the family. And of course, the ionization energy will decrease as those electrons get farther and farther away. It's for this reason that we're able to actually take xenon and form some compounds with that. So here are some compounds that have been formed from xenon. Notice that the element that we're reacting it with is the fluorine, which has a very, very high electronegativity. So it's about the only thing that can actually pull electrons away from the xenon to form these covalent bonds. Xenon difluoride, xenon tetrafluoride, xenon hexafluoride. So the xenon tetrafluoride is what's shown in the picture here, the crystalline structure of that. Chromium actually will form a stable compound as well with the fluorine, the chromium difluoride. And let's see, it looks like there was an unstable compound of hydrogen, argon, and fluorine that was synthesized in 2000. So this compound was synthesized in Finland, but it was highly unstable, so it wasn't there wasn't much practical use for it at the time. This wraps up our study of the periodic table and the periodic trends. So the next thing we'll be moving on to is bonding. So we'll get into that in the next unit.